Section 2.4, Equations of Kinematics of Motion for Constant Acceleration. So before we get into these key equations that are awesome super equations, we're first going to simplify our notation a bit. So since we're just dealing with one-dimensional motion, we know it's just one dimension. Instead of writing these boldface V's and X's and A's and drawing in all these arrows on top, which is really tiresome, we often will just simplify to write a V without the average, without the arrow on top, without the boldface. So we're going to leave off all of that for the displacement, velocity, and acceleration arrows. We will still care about direction. We'll care if it's in the positive versus in the negative direction. So it's not that the direction no longer matters. It's that we already know it matters. And so rather than explicitly being like, direction, we're just like, oh yeah, velocity, it has direction. So we can just write it as a V. So that's one note. And it definitely helps in trying to write all these things out. So now we want to get to these equations of kinematics, which, as I alluded to, are pretty awesome equations. So let's take a look at the first one. This is the derivation of how to get there. If you don't like derivations, you can just steal the end result. So we're going to say for these equations that the clock starts at 0 seconds. So that won't always be the case, but for these equations, it simplifies them so we get them in a nicer form. Let's look at our equation for acceleration. And it's acceleration is equal to v final minus v initial divided by t final minus t initial, but t initial is now just 0. So we have acceleration is v minus v naught divided by t. Well, if we want to rearrange this a little so that there's not a fraction, we can multiply the t across, so that's up by the acceleration times time, is equal to the difference of velocity, v minus v naught. And if we add the initial velocity to the other side, we now have an equation for the final velocity, that the final velocity is equal to the initial velocity plus the acceleration times the time. This is a really useful equation, so you definitely will want it on your equation sheet, guarantee it. So there's the first of our kinematic equations. Let's keep going. Another consideration we can make is that in addition to starting at time is equal to 0 seconds, we can also start at the origin. We can define wherever we start is at x equals 0. So then if we go to our average velocity equation, this one we will specify that's the average velocity because before the average acceleration, it's constant acceleration, so that ends up not mattering. But here, average velocity is equal to the final position minus the initial over the final time minus the initial time, or it's just x divided by t. This is much simpler, right? Because we set the other two equal to 0. So if we multiply the t across, we get that our position at some given time is equal to the average velocity times the time. Well, average velocity, another way you could calculate it is you could take the final time plus the initial time and just divide it by 2. That's taking the average of the two velocities. So this is another equation that sometimes is useful. In many cases, it's not as useful as the others, but it is still one of the super kinematic equations, so it's worth noting. One more that we're going to derive here. If we start with our equation for velocity that we derived and the equation we just derived for position or displacement, and we substitute in the result we got for velocity into the v final here, we can get another equation that's 1/2 v naught plus at, all of that times the time. So we distribute the time out, right? And we get this other super equation. This is one of my favorite equations. It tells us that the final position, or the displacement, is equal to the initial velocity times the time, plus 1/2 the acceleration times the time squared. You have to remember that square there. It does matter. And so this one will pop up quite a bit. What you may be starting to notice is that we have the same variables appearing here. These are known as our kinematic variables. Its displacement is x, acceleration, which is constant. It's only going to have a single value for these equations, and that's given by a. The final velocity at some time t is given by v. The initial velocity when t is equal to 0. and then the elapsed time, t. So these are the main 5 variables you'll have to identify, and I encourage you on these problems to write out all 5 variables and see which ones you can, you know versus want to know. We'll get more into that in just a moment. So here are all 4 of our kinematic equations. There's one more that we didn't derive together. I'm happy to go through this with you if you're interested, but it's not necessary. You can take the end result. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. So these 4 equations, definitely one on your equation sheet. We'll be using them all semester because they're basic equations to describe motion around you. And the interesting thing about these 4 equations is that they all have 4 out of 5 of our kinematic variables from the previous slide. So they're all missing one of the 5 kinematic ones, right? So this top one has no mention of displacement x. Now, that doesn't mean if you want to find displacement, you use this one because you're like, oh, I'm missing displacement. No, that's saying if the problem doesn't mention displacement and you don't care to find out about it, you probably want to use this top equation because you don't have to deal with displacement. Or if you don't want to deal with time, ain't no one got time for that, then you can use this bottom equation that doesn't have time. It just has velocities, acceleration, displacement. So that's a really good problem-solving strategy. And that actually brings me to this next slide, which is a reasoning strategy, where you can say, okay, how in general do we want to approach these problems? Because at first it will feel like they're all totally different, but the more you learn physics, the more you'll see that there really is this overarching structure. And you want to try and tap into that because then it becomes less overwhelming. You're like, oh, it's just this sort of problem. And if I just follow this procedure, we're good to go. So this gives you a procedure that you can follow in approaching them, and it makes it less overwhelming. So reasoning strategy, first you want to make a drawing. So draw a picture, right? And then on your drawing, decide which directions are positive or negative. So this is still part of the draw part. Then write down the values that are given for any of the 5 kinematic variables. Write down what you know. You're going to verify the information contains values for at least 3 of the 5 kinematic variables. If you have 3 of the variables known, you're good to go on these problems. It's amazing. Identify the desired unknown variable and select the appropriate equation. So the unknown variable is what you want to solve for. The appropriate equation is the tool you're going to use to solve it. Number 5 is an interesting point. When the motion is divided into segments, remember that the final velocity of one segment is the initial velocity for the next. So that's under tools or the know information. You might want to rewrite your knowns for the second segment versus the first one. And then to keep in mind, there may be 2 possible answers to a kinematics problem. So you always want to check and make sure that what you have is actually reasonable, that it makes sense. You don't just say, cool, my calculator gave me an answer, I'm going to write that down and move on with my life. You want to go, wait, okay, connecting back to reality. Is this reasonable? So let's check out an example of this reasoning strategy in practice with a speedboat. So a speedboat has a constant acceleration of plus 2 meters per second squared. The initial velocity of the boat is 6 meters per second. Find the boat's displacement after 8 seconds. So this is where I'd really encourage you to make a picture, right? So we have a picture of a boat here, but you can draw your own, right? And it'll be super impressive like mine, I'm sure. Right, so we have a boat and it says it has some initial velocity of positive 6. So it's moving in the positive direction. And we want to find the boat's displacement after 8 seconds. So if it's moving in the positive direction, I'm going to guess that's over here. Right, and so I'm going to also label that this way is the positive direction versus the negative, following that draw technique. And so this is a decent picture to start, kind of rough, but then we could write down everything that we know here because they give us quite a bit of information, right? They give us this acceleration and they even tell us it's in the positive direction. So plus 2.0 meters per second squared. The initial velocity, v0, is plus 6 meters per second. And notice there's also this 8 seconds. What is the 8 seconds? Well, it'd be tempting to say, well, the closest parameter to 8 is displacement. But is the 8 seconds displacement? It's not, right? And the clue here is the units. The units are seconds. That has to be our time. The displacement is actually tied to what we want, right? And remember, what's our variable for displacement? We are going to use x. All right, so we know our acceleration, our initial velocity, our time. We want to find x. So if we're thinking about which tools to use, what variable is missing that we don't care anything about? Well, notice there's nothing about the final velocity. So we want to find an equation that does not have the final velocity. So we could even go back and check, right? If we swing back through our slides, which one does not have velocity? See, the first one's missing displacement, the second one's missing acceleration. This third one does not have final velocity. So that's the equation we're going to use. And conveniently, it's even set up to solve for displacement. But even if this problem was instead asking for initial velocity or acceleration, we would still want to use this equation. We would just need to do some algebra to rearrange it. But in this case, we do not need to use algebra. We can just plug and chug away. So let me get my drawings out of the way. So we have the initial velocity, 6 meters per second, times the time, 8 seconds, plus 1/2 the acceleration, 2 meters per second squared, times 8 seconds. Again, this acceleration is squared, and that's part of why I really encourage you to write the equation out explicitly in symbol form, right? Writing all those weird symbols before you plug in numbers, because then you can look back up here and be like, oh yeah, it was t squared, right? And you're less likely to forget that square there. You still might forget it when you're plugging it in, which is why writing this out explicitly helps. And that's where units can help, right? We can check our units. We have meters per second times second. So with this first one, we'd see that the seconds cancel. With the second one, it's meters per second squared times seconds. So if we just multiplied 2 times 8, we would cancel one of those seconds, but not the other. And that's where the square matters, that both the seconds are squared and the 8 is squared. So you'll want to make sure when you plug in your calculator that it's 8 squared. And it's only with the square that the seconds will properly cancel out. And you're left with the desired units of meters, that this is indeed 110 meters. So that gives us one example of using these kinematic equations. Let's look at one more, just so we can get a little more experience. The physics of catapulting a jet, which just that sentence is amazing in itself. I hope you appreciate that. Like, picture this, wow. So a jet is taking off from the deck of an aircraft carrier, as the figure below shows. Starting from rest, the jet is catapulted with a constant acceleration of 31 meters per second squared along a straight line and reaches a velocity of 62 meters per second. That's pretty quick. Find the displacement of the jet. All right, so we have a picture here, so we don't need to redraw it. I encourage you to always draw your own picture. Most of the times the homework problems won't include a picture, so you'll need to draw one. Let's keep going, and instead, for our time together, identify what we know. So this is focusing in usually on the numbers, but it could also be any clues given to us in the problem, right? So one number that jumps out at me is this plus 31 meters per second squared, and it says that's a constant acceleration. Acceleration is my A, and that is in the positive direction, positive 31 meters per second squared along a straight line, and reaches this velocity of 62 meters per second. Cool. V, and it reaches this velocity. So is this our final or initial velocity? Since it says it reaches it, I'm going to say that's our final velocity. That's where some interpretation really matters. And that's 62 meters per second. All right, that's all of the numbers that are given to us. We can look at what we want to find. It says find the displacement, right? So what variable do we use for displacement? That's going to be our x. Cool. And so now, as we go to start thinking about tools, we can check what we know. And notice we only know 2 kinematic variables. We want to find a third, but before we can even find the displacement, we're going to need 3 kinematic variables in order to solve this problem. So look back at the problem again. Is there anything else that we might be able to write down as something that we know? First off, we could think, what are our other kinematic variables? That's a good strategy. Do we know anything about time? And do we know anything about our initial velocity? Looking at this, I don't see any mention of time. There's nothing with seconds. Doesn't seem to mention that. But there is a key detail in the initial velocity. That's up here. Maybe you saw it. Starting from rest. If you are starting from rest, that is, the start is your initial. And from rest, what is your initial velocity? It's in fact 0. So that is subtly hidden into this problem. And that's the sort of interpretation that you're going to get very familiar with up to this point. All right, so now looking at this, in terms of our tools, we're going to want a tool that does not involve time, right? So that's what we want to focus on when we look at that list of all of them. It's one that doesn't involve time. And here I can actually show you how to derive said equation. Here, we'll first go back, see, okay, which one does not involve time? Oh, it's this bottom one. B squared is equal to V naught squared plus 2ax. It's the one we didn't yet officially derive. So as we look at it here, we can take our acceleration definition, rearrange it to solve for time, plug it in to our displacement and average velocity one to eliminate time, and then do some math here with distributing, and we derive at this equation. This is just a rearranged version. I prefer to instead start with the given one, which is just that V squared is equal to V initial squared plus 2 times acceleration times displacement. If we want to solve for displacement, we're going to need to subtract the V0 by both sides. So V squared minus V0 squared is equal to 2ax. And now to get the x by itself, I'll divide both sides by 2a. Divide both sides by 2a, then we arrive at this same equation here. So it's just coming back from this key equation, one of our basic super kinematic equations. All right, so once we have that equation set up and rearranged, and I encourage you to manipulate it algebraically, to rearrange it before plugging in numbers. It does help eliminate mistakes in the long run, I promise. Then we can just plug and chug. So we have our final velocity squared, don't forget that square, minus our initial velocity squared. Notice the minus is on the outside of the square. So the minus won't be canceled. It doesn't matter in this instance since our initial velocity is 0, but that is worth noting, divided by 2 and divided by 31 meters per second squared. If you do this properly, you should arrive at 62. If you end up with a huge number, make sure that you've divided by 31. It can be really easy to plug it into your calculator as dividing by 2 and multiplying by 31, and that will give you a very large number. And the units, if we check that, in the numerator we have meters squared per second squared divided by meters per second squared. So the seconds squared cancel, one of the meters cancels, and we are left with the units that we'd expect, which is meters. So this highlights how we can use these super equations in just general situations that have a constant acceleration, where the acceleration has a fixed value. In the next section, we're going to look at a special case of constant acceleration, which is always around you. So stay tuned. There is more good stuff to come.